All right, so let me start recording this again. All right. I will get going then. All right, so the first thing I need to identify is asking for pH. I hopefully know pH equals minus the log of H plus. If I have a strong acid, which HCl is one of the strong acids, remember we just have to memorize those. If it's a strong acid, then I know it's going to totally dissociate. So I'm going to have just H plus and Cl minus, and that's how much. So 2.5 molarity will make 2.5 molarity of this and 2.5 molarity of this. And so that's what I need to do. I would need an ice table if it was a weak acid, but since it's a strong acid, I do not need an ice table. So minus the log of 2.5. It is negative. It's a pretty concentrated strong acid, so it's negative, and I'm not concerned about that at all. Negative 0.3979. So I can see I need to round that to one of these choices, so that would be A. All right, which of the following is a diprotic acid? So this is like as definition-y as they get. Diprotic means there's two hydrogens that can be removed, so that's this one. So in the first reaction, it can lose one hydrogen and then another. But like this only has one hydrogen, only one hydrogen, only one hydrogen. This has more than one, but these ones are kind of tucked in the middle on purpose. Those are not ionizable, so those ones are not easy to lose, so it just has that one as well. So it's just C. Okay, the data below are for an, okay, so basically it's giving me a equilibrium reaction, and it's giving me kind of like an ice table, not the whole thing. And they want me to just answer that number. So I would set this up like an ice table. Don't necessarily need to rewrite all this, like however your brain handles it, but like that's what I'm going to do just to make it clear. All right, so I put in all the initials. And then I'm just going to pretend like I don't have a final, but I would say, so like this is the 2, so minus 2x, minus x, plus 2x. Okay, here we go, plus 2x, like that. And then they gave me one of the finals here. So that means this is equal to 0.5, the change, right? So negative 0.5, 2.5 plus the negative 0.5 would be 2. Which means, I'm just going to kind of write it down here, x would be 0.25. I don't know if I'm explaining that very well, but anyway, hopefully you can see how I got the x is 0.25, and now I know this is 5 minus x, so this would just be 4.75, which is C. All right, so can I go backwards, not write a K from an equilibrium, but can I write an equilibrium from a K? So I just need to remember that it's products on top, reactants on the bottom. So it's F2 and BR2 on the bottom, BRF3 on top, so that's my product, and then I just need to put in the coefficients, 2, 3, and 1, and that looks like this one. So of course I wrote them opposite of how they did, but as long as they're on the correct side of the arrow, that doesn't matter. So that looks like the same answer. Yes.
I just have a quick question. So when I was going through this, I got that same answer, but I was just, what do the P's in front of, like, does that stand for their like coefficients?
No, that would be the partial pressure. So Kp would be an equilibrium constant in terms of partial pressure.
Right.
Normally we think about it in terms of molarity. So the P just means it's the partial pressure of BRF3. It would be the same, like if I wrote this exact same thing for concentration, it would just be like the brackets instead of the P's. So the P's just mean it's partial pressure. The brackets would mean it's molarity, but it's the same rules.
Okay. All right.
It's just like what actual number you would plug in.
Okay.
Okay, next up, what is the pH of a solution with an OH concentration of 3.1 times 10 to the minus 10? So pH back to this definition of pH up here, except I don't need to worry about anything breaking apart. I already know that whatever happened resulted in this. So I could do this a few different ways. I think what I would do, definitely not the only way to do it, but I would do the POH, which is minus the log of the OH, and then I will subtract that from 14. You could also figure out the H plus with the 1 times 10 to the minus 14th, whatever you want to do. So it's 9.5, and so then I just know pH equals 14 minus 9.5. Which I'm sure I can do in my head, but I'll just make sure I got a real answer. Okay, strongest acid from the list below. There is a rule about this, but actually this one's pretty easy because only one of these, only one of these is not a strong acid. So if I forgot the rule, if I remember that HF is not a strong acid, then I can use that to know that this is the weakest. And so then the rule must be that it increases as I go down. That's honestly how I remember that rule. The HF is not strong, but all the rest are. So iodine must be the strongest if there's a trend at all, and there is. So then that would be D. All right, which of the following combinations cannot function as a buffer solution? I know that I need to have like an acid and then its conjugate base bonded to a metal. It looks legit, all of those look okay. So that's not the thing I'm looking for. And so then the other thing I know is it has to be a weak acid. And so then if I identify right there as a strong acid, then I know that must not be a buffer. All right, so there's page 1.
So just coming back to number 6, does it have to do with electronegativity negativity for like the strongest acid?
Yes, it does have to do with electronegativity because all right, so basically a strong acid would be a weak bond, right? Like you want to be able to pull the hydrogens apart. And so in order to do that, you have to have a weaker bond. And so
it completely disassociates, right?
Right. Well, so this one does not completely dissociate. These ones do completely dissociate. That's what an acid does. So actually, I would think of it maybe not in terms of electronegativity. There probably is an electronegativity like component, but even just in terms of size. If I think about how tiny a fluorine is, when it attaches to a hydrogen, that hydrogen is much closer to its nucleus versus here, the iodine is very large. And so it's easier to pull the hydrogen off because it's far from the nucleus that's attracting it. But the electronegativity may also play a role that it holds on to the hydrogen more because it's a more polar bond.
That makes sense. Thank you.
But if you can pull the hydrogen off easily, that's a strong acid. It kind of sounds opposite, right? Like you kind of think like it must be a strong bond, but that's not it because we want them to separate for it to be a strong acid. So it has to be able to separate easily.
Mm-hmm. Okay. Thank you.
Yep. Oh. All right. Which of the following would decrease the solubility for lead iodide? Okay, so just thinking about what I know about solubility, the first thing that comes to mind is the common ion effect. Like that's an easy one. Other things in here, like would heating the solution, that seems most likely to increase the solubility of a solid. It usually does. Lowering the pH, that could have a role, but I'd have to think about the like pH of the salt, like what that sounds complicated. It might be able to be, it might be able to have a role, but here I see a common ion. As soon as I see that common ion, that's like Le Chatelier's principle, right? So I would shift it back toward, whoops, can't see my marker, but if I add lead from another source, I have too much product because this is what the reaction would be, right? And so if I have too much lead because I put it in from somewhere else, it will shift it back toward the product, less will dissolve. So that would be my best answer. So then I don't even have to think about the pH one. That's a good answer. And then a system is at equilibrium if the rate of the forward reaction is equal to the rate of the reverse, the number of moles is equal to the number of moles of product, the number of grams of reaction equal to grams of product, or it's all become product. Okay, so that one sounds pretty easy. I know it has to do with rate, right? And I know it should be the forward reaction has the same rate as the reverse reaction. And then finally, okay, which would be the best choice for preparing a buffer with pH of 3.5? So we talked about this, that the pH of the buffer is close to the pKa, so that's what I'm going to do. I'm just going to figure out the pKa's for all of these, and that's just minus the log. .4, and I want them to be within plus or minus 1 of the pH. Like they'll only, I guess the pH can only be plus or minus 1 from the pKa, so that's not a good choice. 3, that looks like it could be it. I'm not going to cross that off. There could be a better choice, who knows. 8.6. These aren't really like lined up, but hopefully you get the idea. 3.5, that looks even better. 4.74. That's not good. So really either one, B or D, could be used, but the best choice would be the one with the pKa closest to the pH that you want. So I would pick D for that one. If I was allowed to pick two, I'd pick B and D. All right. Calculate the pH of a 0.04 molar solution of ammonia, NH3, a weak base. Kb is 1.8 times 10 to the minus 5. Okay, so weak acid or a weak base problem, I would approach it the same way. I'm going to start with what is my reaction. That's the first place that these are different. If it was a weak acid, it would just remove a hydrogen. If it's a weak base, which it tells me, right, that it's a weak base, then I add water as a reactant, and my products are the base gets a hydrogen. So I had 3 hydrogens, now I have 4, and the plus sign that comes with it, and I leave behind a hydroxide. And I started with 0.04 of the ammonia. Don't care about water because it's a pure liquid. It won't go in my K, so I don't care. Doesn't really have a molarity anyway. And then it didn't tell me I started with any of those, so I didn't. For my change line, minus X and plus X. And I get to here. For my K, products over reactants, but I do leave off the water because it's a liquid. So 1.8 times 10 to the minus 5 equals X squared over 0.04 minus X. This is where I have to assume X is small. I would do this for a weak acid or a weak base. So that means wherever it was added or subtracted, I assume it's small. Then I can cross multiply. And then I need to take the square root. All right, first I'll just check if X is small. Just make sure it really was. You should always do that anytime you assume that. So I take the X that I got, so the 8.485 times 10 to the minus 4th, and write that, divided by where I ignored it, so that was the 0.04. and then multiply that by 100. It looks like it will be small to me, but we'll just make sure. Oops. You can see 2.1%. There was no 10 to the 0, so I mean, if I want to get rid of it, 2.1%, so that's okay, checks out. And then as far as finishing my problem, I just need to be aware, like what am I actually going to figure out in terms of pH? X is the OH concentration, so I can do minus the log of that, of the POH, then I can get the pH, which is what it actually asks for. So I have a couple of steps left. And I got, oops, sorry, I got off the screen here. All right, so I did the minus the log of my X from down here. That's how I got my POH. Then I subtracted it from 14. Remember, the sig figs are a little bit weird here. It looks like I should really only have one sig fig. That has 2, that has 1. But when I do the log, it's really just the places after the decimal. So I'm not very picky about sig figs on the pH stuff because it's just a little more confusing, but the real best answer would be 10.9. It's not even what I put on the key. I put too many sig figs even on the key, but 10.9 would be best. See, I'll try to put it on one screen. Okay, page 2, done. All right, a buffer. A buffer contains, here's the salt and here's the acid. So I like to just label them. Right away, so when I'm plugging stuff in later, I know exactly where to look. But they have, I know it's a buffer, it says it, because it says it, but also because it has the exact same anion. Here it has a hydrogen, here it has a metal. So it looks great. First up, what is the pH of the buffer? And I did just want to pull up my equation sheet because this is what you'll get on the exam, just so you know, like it is on here, the Henderson-Hasselbalch equation. This is the pH of a buffer. Just don't be confused. Sometimes people try to use this for things that aren't buffers. This is not something that we really have used. I mean, obviously you could do that, or you could just figure out the pH and subtract from 14. So I would not worry about that. But the pH is here. So that's the equation I need. I usually like to just figure out the pKa because I'll need that again in the next parts. So I'll just do that before I get too far. 1.8 times 10 to the minus 5th. Whoops. And now that I have these labeled with which one's the acid and base, I just plug in the numbers. All right, so I got 4.88 for just the straight buffer. All right, when I add 0.01 molar of HCl to the buffer, and this is like what we were doing in that very first problem where I know whatever the concentration of a strong acid is, that's the concentration of the H+. So that's what is going to react here. My H+ will react with my base to make whole acid. H and A together would make the whole acid. And so I can, again, make my kind of modified little ice table here where I plug all those numbers in. And then I get rid of the strong acid. Use it all up. Change signs with the arrow. Hopefully I did them adding and subtracting right. No shame in using a calculator, even though these are you're capable of doing this in your head, but like the decimal places get weird, so feel free. And then I'm back to the Henderson-Hasselbalch equation. I plug in the same thing, but with the new numbers. So now for my base, I have 0.265, and for my acid, 210. I have 4.84. Slightly more, it's not very much. I only added a teeny tiny bit, and so it's more acidic, but only slightly more acidic than my original. Looks great. Okay, and then what will be the pH after 0.04 of NaOH to the original buffer? So just like for the acid, I had or whatever the concentration of the whole acid was the concentration of H+. This is for the OH-. So that's what I care about here. This base is going to react with my whole acid. The hydroxide is going to grab the hydrogen and make water and leave behind the anion. Once again, don't care about water, just using it to balance an equation. All right, and it says it's the original buffer, so the OH is 0.04, that's easy. And then I'm back to these numbers here. So 2 for the whole acid, or 0.2, and then 0.275 for the base. All right. Get rid of the strong base, so minus 0.04, minus 0.04 on the other side of the arrow, plus 0.04. And then I'm ready to use the Henderson-Hasselbalch again. Base on top, acid on the bottom. So 5.03. All right. KSP for calcium fluoride. So first I just want to know like what is going to happen if I put calcium fluoride in water. I'm talking about solubility, so I'm going to be putting this in water, and it looks like I messed up my powers here. This should be a subscript and it should be a superscript, but you get the idea. All right, so what's this going to do? It's going to separate into calcium ions and 2 fluorine ions. That does matter because the coefficients matter. Remember, I don't really care how much solid I have because that doesn't go in my K. And I don't have any of these unless it told you that you had some from another source. And then this would be minus X, and plus 2X. KSP is the calcium times the fluorine squared. And I know my KSP. And then this. And yeah, oh, sorry, there it is. So I just need to take care of this business over here. Remember, the square is like 2 squared and X squared, and there's another X. So this all comes out to 4X cubed. So I'll just get X cubed by itself. And then to get x, I just need the cube root. I always just raise it to the 1/3 power, but you can do, we talked about a few ways you can do that in your calculator in class. .1. For sig figs, I should really just have 2 sig figs, so I rounded it to 2.1 times 10 to the minus 4th. Remember that x is the molarity, the solubility, the molar solubility, right? The unit is molarity because it came out of the ice table, and that how much of this will dissolve is x. So whatever my answer here is the answer for part A. And then, so that's molar solubility, moles per liter. I put big M, which is the same. You could write it as moles per liter, that's fine, either way. But down here, I want to just convert it to grams per liter, so I just need molar mass. So here I do want to write it as moles per liter, so I can make sure I get that set up right. And then I just need to figure out my molar mass. So I've got calcium 40.08 and fluorine is 19, 78.08. And so I set it up so that the moles cancel, so I just have to multiply them. Two sig figs. All I have is grams per liter, so that's it, grams per liter. Okay, a weak acid. Okay, so we did one like this. We did the weak base one before, but this one's a weak acid. Similar strategy, except we just pull off a hydrogen this time. Where is it? Sorry. Oh, yeah. We're just gonna compare, you know, how it's set up. I don't know if I can squeeze this all onto one screen, but my ice table looks super similar. Well, anyway, you get the idea, but I've just got numbers for the acid or the base, zeros for the rest, minus and plus x. So it's really super similar. Just setting up the equations different, and then, you know, I have to do this stuff at the end for the base, but this one's easier. Because I don't have to do those extra steps. All right, so I set up my Ka, products on top, reactant on the bottom, x squared on top, reactant is 0.085 minus x. I have to assume x is small. Cross multiply. Square root. And I got 6.45 times 10 to the minus 6. All right, so two things I need to do. Check if x is small. I can tell right away it's super small compared to that. Like if I subtracted that number, it's not going to change, but I will do my check. .007%, so great. And then I need to figure out the pH. So now I just need to do it up here maybe. Because X at equilibrium, H plus at equilibrium is X, so just minus the log of X. .19. All right. Electrolysis, we were doing this last, whatever day, Thursday, whenever we were together last. So remember, my choices for how I can start a problem like this is either I can start from mass or I can start from amps times time. I have amps and I have time, so I'm going to start from amps times time. I really want amps times seconds, not minutes, so I'm going to go ahead and do that. Once I have amps times seconds, then I can use Faraday's constant. And going back to what you have available to you on the equation sheet, we talked about this. It is here. Faraday's constant is here in two different places. Well, it's in one place, two different units, but neither of them is really how we're gonna get the most use. Another way of saying coulombs is in amps times seconds. Like that's the one, but I'm gonna write it out as amps times seconds. However you want to think about it though. Like in your head, you could convert amps times seconds to coulombs and leave it that, whatever. It just, you know. And that's really 1 mole of electrons. It just says 1 mole, but that's really moles of electrons. So now let's just check units here. Minutes canceled, and then amps times seconds canceled. So now I'm just in moles of electrons only. All right, so then I need to know what I'm talking about in terms of moles of stuff and moles of electrons. So I see cadmium is what we're talking about. We're trying to get cadmium metal. And I can see that the cadmium must be 2+ because I need 2 chlorines to cancel it out. So cadmium 2+ to cadmium. So I need 2 electrons for every, to, balance the charge here. And so that's where I'm getting these numbers from. So this is 2 moles of electrons for 1 mole of cadmium. And then finally it's asking for grams. So I just need the molar mass of cadmium. If I can find it, oh, there it is, 112.4. And I'm good to go. That should give me mass, so I just put it in. Yep, 3 sig figs, 15.7 grams. All right, write an equilibrium, write an expression for the equilibrium constant for the reactions. Okay, so there's not much to remember here except products on top, reactants on bottom, stoichiometric coefficients become powers, and then the big one that we forget sometimes, solids do not get included, and if there were any pure liquids, those don't get included either, but aqueous and gas do. So now I'm ready. Going back to that notation earlier where it was the P's, like I could write that instead of writing an expression for Kc, which is what this technically is, you could call it just K, that's fine. But this is a Kc because it's in terms of concentration. So I could write a Kp if I want to, and I do the exact same thing, but I just put in the partial pressures, only my products, so partial pressure of CO2, partial pressure of H2O, and there are no reactants and no stoichiometric coefficients, but I could also just put those in brackets, Kc and K, whatever, you know, it's the same. Just what number you would plug in is the only thing that changes. The actual, like, how they get plugged in doesn't change. I always just do the brackets and do the molarity though, if I'm in default mode. So that. And then for this one, I need to do brackets because they're aqueous, they're not gases. So I wouldn't want to do partial pressures for sure. So just remember the charges stay, and then the stoichiometric, so there's lots of twos floating around, but some of the twos go in the brackets and some of the twos go out of the brackets. All right, phosphogene, poisonous gas, KP. Okay, so we have the KP-KC thing. I don't have that on here. Okay, that is one I always include because I can't ever remember this equation. And I forgot to put it on the sheet. So if I did it on an exam, I would make sure it was on there. Let me just make sure I got it right.
Isn't it KP equals KC times
Is it
R?
KP first?
Yeah, I think it's KP equals the KC
RT.
times RT to the change in, yeah.
So this is what I always get mixed up, is which one is P and which one is C. So that's why I always put it. It's not a hard equation. I just forget which one's which all the time. So once I know which way it goes, then it's easy. So I would include that as there. So you don't necessarily need to memorize it. Or maybe I'll just add it to the equation sheet before. Probably I'd just include it in a question. But anyway, so then you can just convert. So the only hard part then, once you know that, is picking the right, okay, I guess a few things. Picking the right R. So why do I want this R? What I'm looking for is to convert between, remember we don't use units for our case. But if we did, this one would be some multiple of molarity, and this one would be some multiple of atmospheres. So I want the one that has moles and atmospheres and liters in it, which is this one. Remember, there's also the 8.314, but that's joules. That's not going to help me at all here. But these atmospheres I want, moles I want, liters I want. So this is the right version of R, and it's not as intuitive as it sometimes is, where I'm like literally going to be canceling out units. And then the other thing, especially on a huge number like this, I need it to be in Kelvin because it has to cancel with this Kelvin. And even though this is a big number, it's not in Kelvin yet. So I need to add 273 to it to get that into Kelvin. And then I still have to pick the right N. So those were the N was the part I was going to say was the place to get confused, but these are as well. So just make sure this one's in Kelvin, this is the right R. And now my N is how many moles of gas you have, and it's final minus initial. So final meaning products here, so that's 2, minus the initial is just the 1, so that's to the first power. Yes, go ahead.
I'm sorry, can you repeat the delta N part?
Yes. All right, so I got 7.993. It looks like I should really only have like 1 sig fig, or 2 maybe. So 8 or 8.0, something like that. Okay, yes, so the N is the change in the moles of gas. Gas in particular, this is all gas phase. So how many moles of gas do I have? And then delta always means final minus initial. Remember, in a reaction, that would be like products, would be the final state, and the initial would be like the reactants. So I have 2 gases on the product side, and then only 1 gas on the reactant side, 1 mole of gas. Not just the fact that there are 2 of them, but if there were stoichiometric coefficient, like if this was a 2, then it would be N equals delta N equals 0, because that would count as 2 moles of gas. But I just have 1 mole of gas on that side, 2 moles of gas on this side, so 2 minus 1 equals 1.
So the total on the
So then I
side.
raise it. The total on the side, yes.
Okay, thank you.
All right. Let's make sure that's all on screen. Okay, so now onto an electrochemistry problem. First I need E cell, and then I'm going to figure out, so E cell standard, so that's under, remember the standard part means that it's 1 molar. And then they give me some different concentrations, so I'll figure that one out. But I need E cell standard first, no matter what. So what I need to do is pull out my table of potentials. You'll have this whole table on the exam as well. I need to find my relevant half reactions. And then I need to do cathode minus anode. So, okay. Now, there's a couple of ways I can figure out the cathode. It depends on the situation. In this case, they gave me a reaction, and so I need to go with the reaction as written. So I need to identify from what's being oxidized and reduced here, which is the cathode and which is the anode. So this is being reduced. I can see it went from 1 to 0. So that's the cathode. And so then the 0 to 2 plus is the oxidation. That's the one that went up. So that's my anode. So I need to find my silver. It's going to be between silver and silver plus if I see silver more than once. Okay, here it is. Whoops. So that is 0.80. And then I need to find between copper and copper 2 plus. Here's copper plus, so that's not it. Okay, here's copper and copper 2 plus. Okay, so the other ways that you could figure that out is if it didn't give you a balanced reaction, it just said like you have copper and silver, what's going to happen? You would go by the chart, whichever one has the bigger or like higher up, but you know, it's like 2 columns. Okay, so this one's higher up, is the one that should be reduced. And so this should be my cathode and this should be my anode. That's what I got, right? That's what I saw based on the equation. So that means that the way this is written, it will happen spontaneously. But if they're writing the equation, they can write it however they want. It doesn't necessarily have to be spontaneous. So just to like throw out a couple ways you could do it, if you have a reaction, you have to go by what the reaction says. If it doesn't match what the table predicts, then you'll just get a negative E cell and you'll know that's not a spontaneous reaction. But my positive E cell tells me this is spontaneous as written. Okay, so then for E cell not standard, that's the Nernst equation. And the Nernst equation is on here 2 times. It's on here, here and here, but with slightly different, I don't know who wrote this equation sheet, but this is the one that we use at this campus for all the classes. So I'm going with it, but I don't know. So the difference, the real difference is one's natural log and one's log log. But then the other difference is in this one, they've plugged in all the constants, the N, the T, and the F, and this one they didn't. Well, in this one, they technically would like plug them in, and then when they do the change of base formula, it's an R, sorry, not the N, the R, the T, the F, and the change of base formula. You can use either one of these equations. I guess I'm going to just do this one because it already has the numbers plugged in for me. So just make sure you pick an equation and then use the right type of log, push the right log button. So that's what I want to use, E cell standard, which is what I just got, and then minus this constant divided by N, natural log of Q. And that should really be a unit of volt. All right, so E cell standard, 0.46 volts. Oh, not equals, minus 0.0592. N, what is my N? N is how many electrons are transferred when the reaction happens one time, or 1 mole of times. So I go back to my balanced equation. If I didn't have a balanced equation, this would be the time to write it. And I can see, I don't know, whatever you want to do, but I'm going to write half reactions just really quick, because then it's easier to see. To cancel the electron, or to cancel the charge here, I have 0 and 2, so I need 2 electrons. Here, I have 2 silver pluses becoming 2 silvers, so I would need 2 electrons over here. So that 2, the number of electrons that cancel, that's my N. And then the Q, what is Q? Q is back from chapter 16, equilibrium, where it's just like an equilibrium constant, but it doesn't have to be equilibrium concentrations. So back to my balanced equation, products on top, solids get left out. Reactants on the bottom, solids get left out. Stoichiometric coefficients become powers. So I think the Q is complicated enough that typically I would just sort of solve it off to the side and then plug it in. I know my equilibrium constants don't have units, so my Q is not going to have a unit either, so I left off the molarities. But I can't forget to square the silver. If you're not sure, if you don't feel confident about like the squaring, the scientific notation, all that stuff, another way, you can separate it into steps. You can divide it by 6.31 times 10 to the minus third the first time, and then divide it by 6.31 times 10 to the minus third again, because that's just what squared means. But if I'm using the scientific notation button on my calculator is smart enough to figure out what I wanted it to do. So either way. All right, so that's 14.4. And then again, this is just like, especially if you put this in here, like it's just bulky. It's just a lot to put into a calculator at once. So a lot of times I'll just plow through and put everything in my calculator in one shot. I don't really do that here. I would probably break it up. So I would probably just do the natural log of that. Oh, no. I was supposed to, oh, see, I did the wrong thing. LOG log. I didn't copy it down right. I decided to use this one, so I need the LOG log. So LOG 14.4 times 0.0592, and again, I'm going to double check since I didn't copy one thing right. I'm going to make sure I got that right from the sheet, and then divide that by 2. All right, so that's this. And then just be careful with the units. I did not include that negative sign yet, so this is just the number for this. And so I'm going to do 0.46 that I got from the previous minus that answer. No more room, but I got 0.43. And if you're really paying attention to the units, you might be wondering what happened to my moles here. These really are volts per mole, because remember, it's all for 1 molar, so like per 1 molar of reaction and all that. So sometimes you see per mole and sometimes you don't, and so I don't usually write it, but you could. But then you just have to recognize this has it as well. All right. Back to equilibrium. All right, so there was one like this on the quiz, and some people got it and some people forgot to do an ice table. And the reason I read this and know I need an ice table is it says a mixture of some stuff is placed in a container. That's initial. I can read between the lines there and say that's initial. And then the equilibrium mixture has this. If I have some initial and some equilibrium, I need an ice table because I can only plug in all equilibrium into my K. And that's what I'm trying to get. So I need to do an ice table here. Remember, if they didn't tell you you started with it, you didn't start with it. So for HI, I know I didn't have any. I like to do it with X's first. You don't have to, but I'm going to do it like that just to make sure I get my stoichiometric coefficients in my head correctly. And then here's what I know about equilibrium is that I have 1.87 times 10 to the minus 3. And that, I went from 0 to that, so the 2x, the change is it went up by 1.87 times 10 to the minus 3. So I can divide that by 2 to get my x. Oops, I didn't actually do it though. So that's the number 9.35 times 10 to the minus 4 that I need to subtract here and here. I didn't write this very big, but you get the idea hopefully. So 1 times 10 to the minus 3 minus 9.35 times 10 to the minus 4. It's 6.5 times 10 to the minus 5. And then this one is 2 times 10 to the minus 3 minus 9.35 times 10 to the minus 4. 1.065 times 10 to the minus 3. And then this one already was my equilibrium amount that they gave me. So now I'm ready. I just need to write my equation. Products on top. Sorry. Reactants on the bottom. And I don't know what K is. That's what I'm trying to figure out. So now I just put in these numbers from here. 1.87 times 10 to the minus 3. 6.5 times 10 to the minus 5. 1.065 times 10 to the minus 3. Oh, and one of them is squared. Whoops. There we go. 1.87 times 10 to the minus 3 squared. All right, and I got 50.5. We're just checking my sig figs. This has 4, but this one only has 3. So I'll round it to 3, 50.5. Okay. Le Chatelier's principle. So I want to just sort of get the situation figured out here. Excuse me. 2 gases on the left becoming 2 gases on the right. Nitrogen, oxygen, and nitrogen monoxide. Okay, so what's going to happen? What if I add helium to increase the pressure of the system? So if I increase the pressure, it's going to shift toward the side with less moles of gas. Oops, sorry. There we go. But I have 2 moles of gas over here and 2 moles of gas over here, so no change. Right, nothing should happen. If the reaction mixture is heated, and here they told me the delta H, so I need to use that information. So this is a positive delta H. That means it's an endothermic reaction. That means heat is getting used like a reactant. So heat should go over here. And now I can think of it like a reactant. If I increase the reactants, it will shift toward the products. What if I remove NO? That's a product. If I remove products, I won't have enough product. I'll need to make more products. So that's a shift to the right. hopefully I at least know that these should be opposite, right? NO removed, NO added should have the opposite effect, and it should. If I have too much product, I should make more reactant, shift to the left. Volume of the container is cut in half. That's just like this pressure one. I mean, it's not just like it. It is just like it. This one would give it less room to move. This one would give it less room to move. So they should have the same answer, but especially in the case where they don't change, any pressure or volume effect would not change it. But when O2 is added to the system, that's a reactant, so it should shift to the right. All right, and then unless I'm missing a page, we're on the last one. Okay, so complete and balance the following redox reaction. So to balance a redox reaction, step one, separate it into half reactions. So I don't care about oxygen or hydrogen. That can go wherever it needs to, but I need lead to be all in one reaction and chlorine to be all in one reaction. So just make sure everything's on the correct side of the arrow. Balance anything that's not oxygen or hydrogen. So this is one lead, this is one lead. Ignore the 2+, that's just a charge. That doesn't count how many it is. So one lead, fine. One chlorine, two chlorines. So balance that. Then I balance any oxygen with water. So I have two oxygens on the left. I'll need two waters on the right. Balancing the hydrogen, I use H+, so I have 4 hydrogens on the right. And there's nothing down here, by the way. There's no oxygen, no hydrogen. So I'm just letting that one alone for a while. Balance the hydrogen with H+. And now I need to balance the charge. Remember, if there is no charge written, then it's just neutral. So like this is neutral, this is neutral, this is neutral. And then I want to figure out the total charge on the left. So this is 4 hydrogens plus 0, so 4 plus. Lead 2+, and 0, so this is 2+. And I need to use electrons to make the charges equal, so I need 2 electrons over here. Down here I have 2 minuses over here and 0 over here, so I need to balance that with 2 electrons to make that 2 minus. Then I need to make the electrons cancel if they don't already. Right now they do, 2 electrons on the left, 2 electrons on the right, so that's done. And then I just add them together. Canceling anything else. Now there's not much that cancels in this one because there was only water and hydrogen in one reaction, not in both. But if they were in both, then I could cancel those. But okay, this is in acidic solution right now. Before I switch it to basic solution, I want to make sure it's balanced. I don't want to bother going any further if I made a mistake. So I want to check my elements. I've got 4 hydrogen, 1 lead, 2 oxygen, 2 oxygen, 2 chlorine, 2 chlorine. So that's all good. And then total charge on the left, total charge on the right. So this is 4 plus, 0, and 2 minus. So that's a total of 2 plus. 2 plus, 0, and 0, so that's a total of 2 plus. So this is balanced. Because I have H+, this means it's acidic, right? If I have extra hydrogen floating around. Since they specifically told me it's basic, let me just change colors here so I can sort of try to make clear what I'm doing. I need to get rid of the hydrogen. I'm going to do that by adding 1 hydroxide for every hydrogen. So then I wrote that not very well. There we go. Plus 4 hydroxides for my 4 hydrogens. Because this was a balanced equation, if I do it to the left, now I need to do it to the right. Otherwise, it won't be balanced anymore. So 4 hydroxides over here. And then these 4 hydroxides will bond with those hydrogens and become 4 water. Now, all I need to do is cancel stuff. I see I've got 4 water on the left and 2 water over here, so I can do that. And now it's kind of a mess, so let me just rewrite it. 2 waters on the left, lead oxide, 2 chlorines. So I got my 2 waters, my lead and my chlorine, my lead, my chlorine, and then I got these 4 hydroxides over here. It should be balanced. I don't think I messed anything up, but it's easy enough to check my work that I should do it. 4 hydrogen, 4 hydrogen. All right, this is 2 oxygen plus 2 oxygen is 4. Here's my 4 oxygen over here, 1 lead, 2 chlorine, 2 chlorine. Total charge over here, this doesn't look very much like a, there we go, 2. Total charge over here is 2 minus. Total charge over here is 2 plus, and 4 minus is 2 minus. So those are the 2 things I want to check, elements and total charge. So that looks great. That's not what I have on the answer key though, huh? Oh yeah, I have it acidic. Oops. All right, I need to update the answer key. This is the right answer. What I have on the answer key was correct for acidic, but I didn't finish it through to basic. So I'll have to change that. Any questions or any type of problem that anybody would like to see more of? I will say I did print out, there were a couple of slide problems that I did not get to in class on Thursday that I said I'd do in the video. So I'll do those. One of them is converting between E cell and equilibrium constant. And one of them, we did one like this in the practice exam, but I'll do this one too because I didn't get to it in class. Yes, Brittany.
Just have a quick question on the practice problems.
Yes.
So I think it's for chapter, let me see. So chapter 17, number 6. For some reason, I was having a really hard time figuring out the pH. And I don't know if it's because you can't assume it's small, so you have to use the quadratic equation or formula.
Oh, yeah, it might be that.
And so I just want to make sure I'm doing it right.
No, it's actually, let me see, what's the, all right, let me, all right, so this is the one you're asking about? Can you see it?
The number 6. The one before
6,
that.
okay, sorry, I looked at the wrong one.
Yeah, I got 7.
Okay, yeah, I think that is, hold on, let me just do a little. Wait a minute. Yeah, so if I do that one, okay, so what let me just use the paper. And then put that down. Okay, so I just wrote the important things. Yeah, so if I just do it like, so then I know like my Ka would be the x squared, and then I assume x is small, 0.025, and I put in the 0.17. Okay, so I calculated that 0.0 or 0.17 times 0.025, and then took the square root of it. I can see it doesn't look good, right? It's pretty big compared to,
yeah, it looks
0.025.
Yeah, it looks bigger.
And if I check, it's like 200%. So
Right.
it's just too big. It doesn't usually happen for acids because usually the Kas are so small. This is a really high one. So if you'd have to do the quadratic formula for this one. Some of these I put in extra challenges, but it's not to confuse you. I should take that one out because I definitely don't do the quadratic formula. So that's why it doesn't work out. If you did
Okay.
the quadratic, you should get the right answer.
Well, it was weird, and that's why I don't know if I was doing it right, because when I did it, I got a pH of 1.65, but the answer says 1.2.
Yeah, so what it would look like is you'd have to do like this, would like 0.17, and then you divide it, and then you get your thing. But it won't change it by a lot. I mean, it's still like, it's still pretty weak acid, and it's still pretty small. So even though it doesn't look like the pH changes by very much, like it's still, that's a significant change in pH, and so you should get that if you did the quadratic formula.
Okay.
Even though it comes out kind of close. But that is why it's not right.
Okay. Thanks.
I don't write the practice exam or the practice problems to like be so tricky. I mean, they're definitely hard. I'm not trying to make them easy. I'm not trying to make them tricky, but sometimes I write them so long ago and then I forget that they're in there. and so somebody tells me, I'm like, oh yeah, I probably should take that one out. Sorry.
Okay. No, it's okay.
Anything else anybody wants to request? Okay, then I will just go through these problems. So you guys can feel free to stay on the line if you'd like to see these two. I need to change my camera so I can see the whole thing. Or, you know, get off if you're not interested in these, but I will put them for the sake of the video. Okay, so I'm going to do this one first. And again, these were ones that were on my slideshow that I did in class last Thursday, but I did not get to. We didn't have enough time, so I'm doing them now. All right, so this one is kind of like the one that we did in the practice exam. We have to get the E-cell standard, and then eventually we have to get the E-cell not standard, but they don't give me a reaction. And the first things are to write the reaction. And the only thing I know is that I have lead and silver. So how am I going to figure out what the reaction looks like? So what I need is my half reactions. This is one where I'm going to pick, well, so let me just see what I can find. I need lead and I need silver. And so I already found silver earlier. Presumably it's just going to, like, it's just silver. It's the only other one I see is silver chloride. Obviously, I think they would mention if I had chlorine in there. So it's just the silver by itself. And then I need the lead one, which only shows up one time as well. And that's right here. So now I can pick based on, this one is the higher one. So this should be the reduction, which is the cathode. And this is the lower one. So this is my anode oxidation. And now I can, maybe I'll just write my half reactions. I guess that's what I asked for first. So for my cathode, this is written as a reduction. And so that's how it will get written. I don't have enough space, so let me do it up here. But this is my oxidation. All of these are written as reductions. So this one I need to flip it to make it an oxidation reaction. And then like we were doing earlier, separating half reactions and can't, balance anything that's not oxygen or hydrogen. We don't have any oxygen or hydrogen. Make the electrons cancel. So I still do need to do that here. And then that's my answer for the first part. Write the reactions, the half reactions for the anode and the cathode. Maybe I should just label them for good measure. This is my reduction, so this is my cathode. And this is my anode. And those are my half reactions. And then for the balanced cell reaction, it would be the whole thing added together. So 2 silver pluses on the left, lead on the right, 2 silver on the right, lead plus on the right. And then the other thing is I didn't, these don't say, the half reactions don't say phases, but I need to maybe think about that because I'm eventually going to need to do the Q thing and all that. So when it's a metal by itself, no charge, that's a solid, right? These are solids. And these ones with charges have to be aqueous. Those are ionic solutions, those have to be aqueous. So solids and aqueous, just to help me along the way. All right, so then E-cell standard. hopefully easy enough at this point. I know which one's my cathode. That was the 0.8. My anode, negative, so minus negative 0.13. Remember, I flipped this reaction, but I don't do anything with the sign here. I'm not like flipping that. That's what the minus sign is for. I multiplied this one by 2. I don't do anything with that. I just take the numbers straight from the table, cathode minus anode, very straightforward, except that we're used to like multiplying by stoichiometric coefficients and stuff. We don't do any of that here. And so this is minus and negative, so it should be 0.93 volts. All right, so then calculate the E cell if I have these other concentrations. So let me go back to my half cells. This is not written very well for this. So, or I guess from down here maybe it's easier. So the Q is, remember, products on top. This is just like a K, just like an equilibrium constant. Reactants on the bottom. Stoichiometric coefficients become powers. Solids are excluded. And so based on what they gave me here, 0.15 and 0.5 squared from these numbers. This part of the problem, so that's my Q. So again, I just need to pick an equation and go with it. I'm going to just do this one. The E cell standard minus 0.0592 over N log Q. And the E cell standard is what I just calculated, 0.93 minus 0.0592, that's the volts. The N is how many electrons canceled after I made them cancel, so that's 2. And then my Q is what I calculated over here, the 0.6. And I'm just going to put this in pieces again. So log log of 0.6 times 0.0592 divided by 2. This time I did get a negative number. Oh, it's super tiny too. It's not going to be very impressive compared to 0.93, but 0.93 minus that answer. So it ends up being 2 sig figs, 0.94. So it didn't change by much. All right, so that's that one. And then there is this one, which asked me to figure out an equilibrium constant. I don't have any information about equilibrium. All I know is that, well, I mean, it's giving me the equation. There is an equation that relates the E cell and the equilibrium constant. And I know I can figure out the E cell. So that's what I'm going to have to do, is figure out the E cell standard and go from there. All right, so looking at this equation, I see that the iron is the reduction because it went down in charge. The silver is the oxidation. So I need to find those iron 2+ to iron 0. Iron 2+ to iron 0 is negative 0.44. And then the silver is, oh yeah, this one I've been using a bunch, 0.80. So not spontaneous, but that's fine. All right, so now they give me the equation here. I need to solve for k, right? This is my unknown, and it's inside of a natural log. So I need to get the k out of the natural log by doing the e function, the exponential. And I need to do that, but first I have to get it all by itself. So I need to move this stuff over, all these things over. So I'm going to multiply by the reciprocal on both sides. So the n's cancel and the 0.025. So that gives me n times, this is on top and this is on top, so E cell standard, over 0.0257 volts. And then on this side, all I have left is the natural log of k. So that's just the algebra of rearranging this so far. And then I can undo the natural log by doing the exponential function here. Obviously, since it's an equation, I have to do it to both sides. So the exponential of the natural log is what cancels and just gives me k. This is the exponential here. And then I need to just plug it in. All right, so k equals e to the. All right, so n, number of moles of electrons that cancel. I didn't write half reactions here. I could do that, or I can just look at it and see, like, that would be 2 electrons. This would be 1 electron per reaction, and there's 2 reactions, so it would be 2 electrons. So 2 E cell standard is negative 1.24 volts, 0.0257 volts. So the volts cancel, and it'd be the E on my calculator. It's the opposite of the natural log, so it's right on top of the natural log, so second exponential. Then I can put all this in the parentheses together. 2 times negative 1.24 divided by 0.0257. Negative 10 to the negative 42. It is super tiny. As I would expect, it's super not spontaneous, right? So I would expect the amount of product would be very small, and the product is what goes on top. And so small numerator makes a small number. And since I don't expect it to be spontaneous, that's exactly what I anticipate. So it looks about like I would expect. So let me try to put it all together. All right, unless you have any other questions that I can answer, that's the exam, the practice exam, and some extra. All right, then I will see you on Thursday.